And good. What's that? Aha. Okay, people, let's get started. We've got a lot of ground to cover today. This is arguably the most science-y lecture that I'm going to give. All right, and it's in a nutshell how strong the case is that humans are creating dangerous interference in the climate system. The sort of refrain down here in the lower left-hand corner of this slide is, what do I tell someone who claims this is all a hoax? Now, aside from a couple of people in the executive branch, it's kind of hard to find those people anymore. But some of you may have a relative or two that still thinks this way. And it's also useful just to review because it says an enormous amount about the scientific method. The scientific method has adopted evidentiary standards that are stronger than those in most of our decision making. And they've done so through the centuries, really, because this has turned out to be the degree of skepticism that maximizes the rate of learning. But the important point here is that every incentive in science is set up to promote the person who tears down what went before him or her. All right? Every incentive is set up to show that everyone else is wrong. That's the way you really get ahead, not by showing that everyone else was right all along. Okay? So let's get going. Now, there's some definitions here. These definitions, there are a lot of them. You don't need to remember those, but the ones in the bottom, I would sort of think you ought to remember. For this lecture, a watt is a joule per second. 1 joule per second. And a joule is the work done by 1 Newton over a meter, which is roughly the force of an apple falling, because of the famous Isaac Newton story, right? That's, clever. A kilowatt is 1 1/3 horsepower. And so a megawatt, 1,000,000 watts, is roughly 1,300 horsepower, which I have here is 0.81 Bugatti Chiron, which is a car that just is the fastest car in the world right now. It also gets the worst gas mileage of any car in the world by a lot. Its predecessor would go 270 miles an hour, but at that pace runs out of gas in 9 minutes. This one goes 305. They won't say how fast it'll run out of gas, but it's got to be 5 minutes or less, all right? Okay, pre-industrial CO2 was 280 parts per million. It's roughly 410 today, maybe 408 or 407. When I checked the latest Mauna Loa figure, the detector on the top of Mauna Loa, radiative forcing is a net change in the radiant energy hitting the Earth's surface. How much radiant energy, like sunlight, hits the Earth's surface in a unit of time, and that's watts per square meter. Remember, everything shines. All of you, you've been told this all your lives, are shining right now. You're like light bulbs, and you're glowing. And you're just glowing at wavelengths that are beneath those that we can see. If we heated you up to the temperature of a forge, you would be glowing bright white or yellow. And as you cool down, you'd go through orange and then red and then get dull, just like you can see a piece of iron from a forge, until you were glowing in wavelengths we can't see, which is what you're currently doing. And so all of that radiant energy hits the Earth, and it's watts per square meter. Climate sensitivity is the amount of warming per unit of radiative forcing. That is degrees Celsius change in the mean temperature at the surface of the planet per extra watt per square meter of radiative forcing. It's often expressed as the warming from a doubling of pre-industrial CO2, which means up from 280 to 560. How much warming would you get from a doubling of the pre-industrial CO2? And a doubling of the pre-industrial CO2 would cause 3 3/4 watts per square meter of radiative forcing. All right? Climate feedback are processes that amplify for positive feedback or reduce for negative feedback the climate change caused by a unit of radiative forcing. We'll talk a lot more about that. It's the climate feedbacks that have scientists so scared about this. I've been an environmental scientist now for over 35 years. And if I go into a new field, very often when I learn more about it, I get a little bit less concerned. But when I first started working on global warming, I just got more and more concerned because of the number of positive feedbacks that we don't fully understand. And this is true in general. The people who know the most about this issue are the most concerned, not the least. Okay. So what about radiative forcing? A lot of people think they know how the greenhouse effect works, but you may not. Okay, you may, but you may not. Well, this is a long story. But I actually don't have time for this story. I'm going to give it anyway. There was the director, James Cameron, was filming a documentary with, and I'm going to pronounce her name wrong, Giselle Munchin or something, Tom Brady's wife, some sort of a model, right? And was arguing about how this worked. And so the scientist on the project, a woman named Heidi Cullen, called me up and said, Steve, Giselle is saying this, and Cameron says it's wrong, and I'm supposed to know this, but I don't. And it turned out Giselle was actually right, okay? And Cameron was wrong. And it's because this is actually kind of a subtle concept. It's not so obvious. So the Earth is sitting there getting bathed in radiant energy from the sun. The big fusion reactor that is the sun is just piling all different kinds of wavelengths of energy into the Earth. And it's hitting the Earth, and the Earth warms up, and it emits the radiation back into space. And that system over the long term has to be in equilibrium, or the Earth would just have more and more and more and more energy and get hotter and hotter and hotter and hotter, or less and less and less energy all the time and get colder and colder and colder. So incoming equals outgoing at equilibrium. Now you see the little gray band around the Earth. That's supposed to show greenhouse gases. Now what greenhouse gases do is that they absorb radiation from the shining of the Earth in those wavelengths we can't see, just like you guys are all shining now. And that radiation, those quanta of energy go up into the atmosphere, get absorbed by greenhouse gas molecules, and a lot of it gets re-emitted back at the surface of the Earth, okay? So imagine that we increased the thickness of that layer. Now, before we do so, this process is kind of like 1 person per minute walking into a store. That is the rate of energy quanta coming in from the sun. Each one staying a couple of hours as they pinball around inside the atmosphere, getting emitted, getting absorbed by greenhouse gas, re-emitted at the surface, heating something else up which shines again, and so on. They loiter around in the store for a while, and then leaving. And so if 1 person is coming in for a minute and everybody stays 2 hours, that means there's 120 people in the store at equilibrium. 1 comes in per minute, that's 60 comes in for an hour, everybody stays 2 hours, so there's 2 hours worth of people in the store at any one time, right? And think of that as the temperature of the store. That's the amount of quanta of energy trapped in the store by all that loitering. Now we double the greenhouse gas layer, or increase it. All of a sudden, this is like somebody unveiling some kind of gizmo that you want to play with and allowing you to play with it as you're leaving the store. So in this case, I've got a brand new kind of an iPhone, and they give you an hour to fiddle with it. And so everybody now spends 3 hours in the store. So they come in, they shop for 2 hours. When they're leaving, they say, oh, look at that. And then they play with that for an hour, and then they leave. Now what happens is, for the next hour, nobody leaves. But then, the number of the people in the store is going to increase by 1 per minute, up until an hour has passed, and then they start leaving again, and then the same number come in, 1 per minute that leave. But now there's 180 people in the store, because each person is loitering for 3 hours, not 2 hours. So when you thicken the atmospheric greenhouse gas concentration, what that does is it increases the loitering time of quanta of energy near the surface of the Earth, and that increases the temperature. Now, as that is happening, the outgoing radiation is actually reduced, just like nobody leaving the store for an hour. The incoming radiation stays the same. So the signature of global warming is not more energy coming in, it's less energy leaving the planet. All right? Eventually, if the greenhouse, okay, this is my PowerPoint extravaganza there. Those are phone zombies loitering around, okay? Eventually, the system reaches equilibrium again if nothing changes further, and 1 person per minute comes in, 1 person per minute leaves, and you've got 180 people in the store, and so you've got a warmed planet, okay? So that's what's going on here. And that's the wrong thing. Okay, now, what are the greenhouse gases that are causing this problem? You all know about CO2, which is the biggie. This is in 2011, the total amount of radiative forcing in watts per square meter, that's about 1 3/4, caused by the extra CO2 we've added to the surface, to the atmosphere since the Industrial Revolution, actually since the Neolithic Revolution. It was the first start of it. The second most important greenhouse gas is methane, which is the dominant constituent in natural gas. Natural gas is almost all methane, and methane is a substantial fraction of our current warming. The big difference between methane and CO2 is that pound for pound, or kilogram for kilogram, methane is way more potent, more than 100 times more potent as a greenhouse agent, as an increase in loitering, than is CO2. But fortunately, its mean residence time in the atmosphere is just about 10 years. The e-folding time, if you're an engineer, is 12 years. So it's about 10 years in the atmosphere. In other words, if you reduce methane emissions and wait 12 years, the concentration from those methane emissions will fall in the atmosphere by 2/3. You wait 20 years and you're down 90-some%. So methane emissions are reversible in a sense, but they're really, really potent. CO2 stays in a substantial amount of it for hundreds to thousands of years. You reduce the CO2 emission and the atmospheric concentration stays close to the same. So we're with it forever. And so the primary emphasis on CO2 is both because it's the most important greenhouse gas and because of this sort of irreversible and cumulative nature of it. There's one other really important sort of distinction here, and this is the impact of atmospheric aerosols, like some of the soot that accompanies combustion of fossil fuel. An aerosol is a particle suspended in the atmosphere. And particles like dust and some aerosols from combustion have a cooling impact. The net impact of aerosols in the atmosphere now that were put there by people is almost 1 watt per square meter of cooling, which offsets the greenhouse gas warming radiative forcing of over 3 watts per square meter. And so the net impact is about 2 watts. Okay, so warming and cooling. Now get out your clickers and just answer this. This is just to make sure everybody's paying attention. Okay, so read the question and then answer this for me. And of course, you aren't penalized for a wrong answer. Yeah? Yeah, that's right. Okay, I'm going to kill it, so everybody should just push a button. Okay, good. Let's see. So we got 50%. The answer is more than 100%. Okay? It's more than 100% because the greenhouse gases themselves do 3.2 watts of forcing, and it's aerosols, non-gases, that drag down the observed warming less than that. Okay? So the forcing, if it weren't for the aerosols, if we cleaned up the air pollution that leads to the aerosols, the true impact of the greenhouse gases would come out. And that's why actually cleaning up coal emission smokestacks is a great thing to do, because it saves lives. The air pollution kills people, but it actually makes the planet hotter. Okay? So this is commonly misunderstood. I mean, all over the place. I remember I was briefing a group that should know better, included the Joint Chiefs of Staff and all the people in that in the military who were responsible for assessing threats. And they were saying, I don't know how big the effect of global warming is. I mean, maybe it's 50%, maybe it's... No, the answer is more than 100%, okay, if it's greenhouse gases. It's important to understand that. Okay. So how much radiative forcing is this? Well, as I just showed you, the impact of the greenhouse gases themselves are 3 to 4 watts per square meter. How big an impact is that? Well, relative to the total energy usage by humanity, it's gigantic. That's the total energy usage by all humans, energy of all forms. Sometimes people say, well, isn't the warming caused by the extra body heat of all the 7 billion of us? That body heat is many, many times smaller than the total energy usage, which itself is many, many orders of, several orders of magnitude smaller than the radiative forcing we're talking about. So the answer is no. On the other hand, relative to the total sunlight energy absorbed by the surface of the Earth, incoming shortwave minus reflected, that's 240 watts per square meter averaged over the entire world and over the entire year. And so this is on the order of between 1 and 2% of a total budget. Now that doesn't sound like a lot, and thank goodness it isn't a lot. But it still needs to be remembered that the 240 watts per square meter, together with the greenhouse impact of the atmosphere, is what keeps the surface temperature of the Earth what it is, as opposed to the near absolute zero in space. So the 1 to 2% perturbation is a perturbation of that gigantic temperature gap. The gap between 1 to 2% of the difference between minus 270 degrees Celsius and the temperature of the planet, which is on the order of 10 degrees Celsius, right? So it's multiple degrees, right? All right, it's possible to measure the incoming and outgoing radiation of the planet with satellites. And this has some uncertainty, but NASA took this really seriously. This is one of the things that scientists have done to say, is this story really holding up? We can measure the greenhouse gases, we think the theory's right, temperature looks like it's going up. But if this is right, then the outgoing radiation from the planet should be less than the incoming radiation to the planet, and in fact it is. It's 0.6 watts per square meter currently in out of balance, which is 24 times human energy usage, okay? It's also possible to track where all that energy has gone, that imbalance energy has gone. And these are uncertainty bands. Let's see, these things are uncertainty bands. There's high uncertainty in the 1970s, and these numbers are the cumulative impact since around 1970. And almost all of it is in the upper and deep ocean. A tiny bit of it is in the land, and a tiny bit of it is in the atmosphere. So most of the warming that has observed, the stuff that we're experiencing, the stuff in the atmosphere and the stuff in the land, is the tip, literally, of an iceberg, which is primarily in the oceans. The reason that the uncertainty bands get narrower up here is that we have more and more measurements all the time, and that reduces the uncertainty. You may hear from time to time that this is caused by natural phenomena, and one of the most prevalent stories on contrarian websites for decades has been that it's caused by solar activity, as though scientists don't measure the output of the sun. This is the output of the solar irradiance from 1975 to 2010, and there are cycles of sunspot activity. And the point is that the warming isn't caused by this. It's small forcing. The total top to bottom is 0.2 watts per square meter, and we know what it is, all right? It's not increasing monotonically, like the temperature. Now, the reason that scientists are so concerned about global warming comes primarily from the positive feedbacks that we know that exist in this system. Now, what do I mean by that? Positive and negative climate feedbacks. A positive feedback is one that where the addition of the greenhouse gases increases the temperature by a bit. But the temperature then changes something. And that something further increases the temperature. And then the temperature itself causes further changes, and so you have positive feedback. Positive feedbacks are what turned Venus early in her history to change from something that could have supported life to a surface temperature caused by the massive greenhouse gas concentrations in her atmosphere that are high enough now to cause temperatures that melt lead on the surface, okay? Fortunately, we, in this planet, haven't experienced positive feedbacks of that magnitude, which is why we're all sitting here. In contrast, now, these represent danger because positive feedback leads to autocatalysis, leads to runaways, right? Negative feedbacks are the reverse. Increased temperature changes something which decreases temperature, and those tend to be regulatory, all right? So these are self-regulating. And what you want is lots of self-regulating stuff and not runaway stuff. Now, we know about some of these feedbacks. And unfortunately, there's a lot of them, all right? And we don't know well about others. But here are the ones we know about. We know that the direct effect from physical calculations and from measurements and experiments and in laboratories and all this sort of thing, that the direct effect of 0.3 degrees of 1 watt per square meter of radiative forcing is 0.3 degrees Celsius of warming. So you increase by a watt per square meter, and you get about 0.3 degrees Celsius of warming. But there's a thing called the water vapor feedback, where when the temperature goes up, more water is evaporated and gets into the atmosphere. There's a physical law that relates how much water vapor can be held in the atmosphere as a function of the temperature of the atmosphere. And this law shows that there's an exponential increase in the amount of water that can be held in the atmosphere as the temperature increases, which is why, incidentally, why Houston keeps getting flooded. Okay, there's scientific attribution studies that trace the big, heavy rainfall events, like the one we just experienced in Hurricane Harvey a couple years ago, to this effect. So water vapor is itself a greenhouse gas. So when the temperature goes up and more water vapor gets into the atmosphere, then the temperature goes up further, which causes more water vapor to get into the atmosphere, which causes the temperature to go up further, and eventually this thing kind of peters out, unfortunately. So global warming increases the concentration. This is positive feedback, and so you get another 0.3 degrees from this water vapor feedback. And that's the uncertainty on the 0.3 degrees Celsius. Okay. There's a second positive feedback called the ice albedo feedback. And the ice albedo feedback says that when we increase the temperature near the surface of the Earth, the ice-covered areas like Antarctica and Greenland get warmer, and we reduce the amount of ice. We also reduce the snowpack. And the snowpack is extremely reflective. The ice is extremely reflective and reflects sunlight back into space. And so when you decrease the ice and snow-covered portion of the planet absorbs more energy. And so this is called the ice albedo feedback. It's also a positive impact, and it gives you another 0.1 degrees Celsius, plus or minus 0.03. Finally, there's a thing called the cloud albedo feedback. And this, for many years, has been the darling of contrarians. The point about the cloud albedo feedback is we know quite a bit about it, but not enough to constrain it as either positive or negative. Whoops. Too many buttons. 0.1 degrees Celsius, it's thought to be positive, but plus or minus 0.23, meaning it could be a positive feedback that causes 0.13 degrees of cooling, or a positive feedback that causes 0.33 degrees of warming, all right? So what is this thing? Well, warming changes the abundances of different kinds of clouds, which change the reflectivity of the clouds, which either absorbs more energy if it were a negative feedback, or either reflects more energy if it's a negative feedback, or absorbs more energy if it's a positive feedback. And so this is still uncertain. On balance, it's thought to be a positive impact, but notice that this number, even with its uncertainty, is small relative to this well-constrained total of 0.3 plus 0.3 plus 0.1. All right? So collectively, if you put all this together, it means that if we were to double pre-industrial CO2, which means adding 3.7 watts per square meters of forcing, that it would roughly increase the amount of warming. That radiative forcing increase would increase the amount of warming by about 3 degrees, plus or minus about 50%. Meaning a doubling of the pre-industrial CO2 would change the mean temperature from 2 to 4 degrees Celsius, okay? So that's what's going on there. And that's primarily, more than half, caused by positive feedbacks, all right? Now, do we have any evidence other than direct calculations for this? And the answer is tons, okay? And so the big deal in science is to come up with an independent way of measuring something, all right? Because what you're trying to do is show that everyone else who went before you is wrong. And then you get like super famous, and maybe you win a Nobel Prize, and then they give you like several $1 million, which then you can give to your kids and that sort of thing. And so there's been a lot of this. And so how can you do this? Well, you can say, well, every once in a while a volcano goes off and discharges an enormous amount of stuff into the atmosphere, and then the climate responds. And it either responds according to these calculations or not. So we ought to be able to measure that. You can. And that's what's going on here with volcanic eruptions. So there are a whole bunch of different ways to do this. Approximately, there's 6 quasi-independent estimates. This is a figure from the IPCC report, the Intergovernmental Panel on Climate Change, which is a group that doesn't create new science, but it reviews the scientific literature every few years as part of the UNFCCC, the United Nations Framework Convention on Climate Change process. And so the most recent full report is the so-called AR5, which was released in 2015. And so there were 6 quasi-independent estimates. This is the climate sensitivity that was estimated. That's 3 degrees. Each one by itself is uncertain, but if you put them all together, they're all in the same place, confirming about 3 degrees of climate sensitivity. Now, how quick does this climate sensitivity, does the warming follow from an increase in the greenhouse gas concentration? And the answer is either quickly or slowly, depending on how you look at it. This is an experiment that was actually done in a climate model. The modern climate model was invented by a guy named Suki Manabe about 2 miles from here. Okay, not too surprising. This is another Princeton thing. And since then, every climate model in the world verifies this thing, right? And what's done here is that in a climate model, you instantaneously snap your fingers and double the atmospheric CO2 concentration, and then you ask, how quickly does the planet warm? And what happens is that about 2/3 of the warming comes in the first 100 years, but the last third takes 2,000 years. Now, what's the slow bit doing? What's going on with that? And the answer is pretty simple. Everybody know what this is? This is the so-called thermohaline circulation of the oceans, all right? If the really lousy movie that you can only see like on bad cable TV, The Day After Tomorrow, was about this thing, all right? It's a Kevin Costner movie. Have you ever seen it? Give it a pass if you haven't, okay? So what's going on here? It turns out there's one place in the world up here where the ocean is both deep and really, really cold. And it turns out that cold water sinks. And so that's the drain of the world. And as the water goes into free fall and falls 2 miles there, it pulls water along the surface up to rush into the drain. And that sets up this tremendous global circulation of water in the oceans. Now, the red is the surface stuff, and the red stuff is a thin layer, like 100 meters thick. Think of it as 100 meters thick. Now, in your mind's eye, you can see a stream, and you're canoeing down it. And if the stream gets shallow, it gets fast. That's where the rapids are. And so this water is moving fast. When it sinks into the abyss, which is 2 miles deep, it's like coming out of the rapids into a deep part of the river, and everything slows way down. It takes 1,000 years on average for the water to traverse the blue part. And so it takes 1,000 years to warm the planet fully, because you got to warm up all that water. All the water coming up from the blue, like here or here, is coming up with water that went down there 1,000 years ago before we put greenhouse gases in the atmosphere, and its temperature reflects that, and it's got to get warmed up on the surface, you see? So that's the long time scale here. So what are the dominant uncertainties about climate change? One we've already mentioned, the cloud albedo feedback, which is largely responsible for the roughly 50% uncertainty in the atmospheric forcing. It's a big piece of it. A second piece, though, is, and you can't forget this, it's not part of the physical system, but it is a dominant uncertainty about climate change. It's, what are future emissions likely to be? This is a diagram from the latest IPCC. That's 1980, that's 2100. This is the amount of emissions from the world in gigatons of CO2 per year. That number's 100, that number's 0. And all of these different lines are different emissions that come from scenarios that the IPCC social scientists view as plausible. Meaning that we don't know what we're going to do as a species yet. It could be that we'll finally take action and limit warming to 1.5 degrees Celsius. It could be also that we don't take action and we really get a runaway temperature change and we get enormous emissions still. So what emissions in the future do is really now the dominant uncertainty if you want to think about the combined social and natural world. The other big feedbacks are carbon cycle feedbacks, and I'll discuss these primarily next time. I'm just going to mention one. There are literally trillions of tons of a CO2's worth of carbon stored in the soils in the far north. Some in the far south, but there's so much more land in the far north that it's in the far north. All that peaty sort of permafrost and stuff up there. Now, we currently emit about 50 billion metric tons a year, so trillions is is many, many years worth of emissions. Now, the reason we have refrigerators is so that vegetable and other matter that we put in them doesn't re-enter the atmosphere before we eat it, okay? Organisms eat it, bacteria and fungi, and return it to the atmosphere. And we're trying to stop that. That's why we put them in cold temperatures. And so the organic matter has piled up in the far north because it's in the fridge. It's organic matter that got thrown in the fridge. And global warming is like leaving the refrigerator door open. All of it spoils, re-enters the atmosphere, and that's what is going to happen to the organic matter up there if we let the temperature rise too far. And that's a positive feedback, and a big one. You can get going a positive feedback that would release much more CO2 than we emit from fossil energy. So, carbon cycle feedback, some are positive and some are negative. The net on the planet is currently negative. We know that. We know that because what we emit from our human activities, half of it, a little over half of it, gets absorbed by the biosphere and oceans. So some of those carbon cycle feedbacks, so the sum of those carbon cycle feedbacks is negative and is currently mitigating about half our anthropogenic emission. Its future, though, is highly uncertain. We don't fully understand it, and so we'll discuss these in the next lecture. This is one of the primary causes of disquiet for scientists who worry about this, because you could get a positive feedback going that you know the mechanism is there, you just don't know when it gets launched. Now, in addition, it's useful, I'm going to just run through quickly the independent lines of evidence that the case for global warming rests on. If you look at contrarian websites, they will have you believe that much of it or all of it is the outpouring of models, of uncertain models. And that's simply false. There are various ways to put this into hoppers. I do it in three. The first is evidence from the distant past. And a lot of this is also a Princeton thing. There are all kinds of ice cores stored over in Guyot Hall. You go down to Antarctica. This is an ice core record that goes back 800 million years. I think the oldest ice in Guyot Hall now is about 2.5 million. Okay, we've been paying for finding older and older ice. Now, why do you want to find ice that's old? It's because air bubbles get trapped in it. And so ancient air gets trapped in it, and you can measure the CO2 in that ancient air. And you can also measure the isotopes in that ancient air and some other things and figure out how cold it was, right? And so you get a record, simultaneous record of greenhouse gas concentrations and temperature going way back. And what you can observe here, that's zero. That's 2014 when we were just under 400 parts per billion. Now we're at about 410. And as you go back in time, you see that when the CO2 concentration goes up, the temperature in red goes up, right? Each time the CO2 goes up, the temperature goes up. They go up and down together because of these geologic and, turns out, astronomical processes. We know what kicks this off. Turns out the Earth has orbital variations that are responsible for this cyclic activity over the last 3 million years. But the point is, in the distant past, when the CO2 has gone up, the temperature goes up. When CO2 has gone down, the temperature's gone down. If you look at the warming now, it's just way, the red would shoot way up. This is also true if you look at less certain proxies much further back in time. This graph covers the last 400 million years. And the blue shows periods of intense glaciation. And this stuff down here shows proxies for the reconstruction of temperature, okay? And what you can see is that it's warm, like during the age of the dinosaurs, the age of the amphibians, when there aren't any, CO2 is high when there aren't any glaciers. And the CO2 is low when there are glaciers. That's what this thing is showing. And there's also reconstructions for temperature that do the same thing. So as far as we can tell, into the distant past, and there are also proxies that go back billions of years, Whenever the CO2 has gone up, the temperature has gone up. And whenever the CO2 has gone down, the temperature has gone down. All right? So now we're putting the CO2 in the atmosphere. All right? Now, a common argument by those who claim that the scientific consensus is suspect is that the climate has always changed in the past. I was just talking with somebody today outside of class who said that, the story was, isn't this just cyclic, right? Isn't the temperature change just cyclic? This is the story from, he wasn't saying he said this, he was saying that this is what, deniers say. And should the fact that the climate has repeatedly changed in the past make you, A, more concerned about fossil emissions or less concerned? That's the argument. So the argument from deniers is, it's always changed, right? It should just make you more or less concerned. This is, again, a are you paying attention question. Right. Okay, finish up. Okay, I'm going to kill it. 3, 2, 1, 0. And the answer, 90%, is more concerned, and that's the point. If it's always gone up in the past due to geologic and astronomical processes, orbital processes, whenever the temperature, CO2's gone up, the temperature's gone up, and whenever it's gone down, the temperature's gone down, and all of a sudden we're the ones increasing the CO2 in the atmosphere, we shouldn't be surprised when the temperature goes up, okay? That's the point. The fact that it's always gone up and down together in the past should make you more concerned, not less concerned. There's no question about it that the 100 and some odd parts, 130 parts per million we've put into the atmosphere since the Industrial Revolution, there's no question that that's anthropogenic because it has an isotopic signature, fingerprint of fossil emissions in it. Okay. The second group of evidence is the records from the historic past. And here, this graph shows the 3 dominant anthropogenic greenhouse gases, CO2, methane, and nitrous oxide, over the last 2,000 years, and you can see they all shot up together. And this is the record of the global mean temperature from 1860 to 2019. This is from that group Berkeley Earth that was set up by Koch brothers funding to try to falsify the global warming story, and you can see it didn't. There are also lots of other records from the historic period. We don't need to actually dwell on this, but there are all kinds of other things that are predicted from global warming. Changes in snow cover, changes in sea ice, changes in rainfall, and so on. And so there are many, many, many independent records that go along with these temperature changes that are from the historic period. It's a many-dimensional data set. Now, I'm going to jump to this one. The point is that, you might say, well, when the ice albedo feedback, we ought to be losing ice in Antarctica. How serious is this, the fact that we're losing ice in Antarctica and the seas may rise? And so one of the things you do is you go out and you put gauges on the snow and ice in Antarctica. And it's really complicated because when the atmosphere warms, there's more water vapor in the atmosphere, so there's more snow added. But in places where it's cold enough or where it's warm enough, you're losing ice. And so those calculations show, and those data sets show, that Antarctica and Greenland are losing ice. But it's possible to argue that, that's a really complicated calculation, and maybe you're just wrong. There are some glaciers that are actually growing because they're getting so much more snowfall, and you can point to those on a contrarian website and say, see, this glacier is growing. So scientists looked for other ways to do this. And one way they looked for it was they launched a satellite. NASA launched a satellite called GRACE, and GRACE measures extremely precisely gravitational anomalies at the surface. And what happens when there's ice on the surface is it weighs something and it tugs a satellite down towards it with more gravity. And when the ice melts, that tugging decreases. And so with extremely precise measurements, the GRACE mission was able to measure integrated ice loss across Antarctica and Greenland. And these are the data, and what they show is that the ice loss is going down and at an accelerating rate. But scientists still aren't satisfied. You're still trying to show everyone else is wrong, because this satellite is a complicated thing. Maybe its sensors were drifting. God knows what could go wrong with it. And so a guy named Walter Munk, who just died, who was, I think, in his 90 at the time, said, you know, the water frozen in ice at the poles, as it melts, it gets distributed around the world's oceans, which are kind of thickest at the equator, where the Earth is roundest, right? Most of the ocean is at the equator, and only a little bit the poles, because they're kind of small, because it's a ball, right? And so that means that it's a transfer of mass from near the axis of rotation to the surface far from the axis of rotation. And that should, just like an ice skater putting her arms out slows her spin, it should be making the day longer. It should be slowing the rotation of the Earth. And it's like, whoa, you know? And so, fortunately, then there are atomic clocks. And nobody had thought to look, but you look back at the atomic clock record, and the Earth's rotation is slowing down at precisely the rate it should be from the Grace instruments. And so that's then a third independent body of evidence for the peril of ice loss. Okay. Final thing is from models. We'll talk more about this later. These are models of the climate, like the ones that are built here at the Geophysical Fluid Dynamics Laboratory at Princeton. The way to read this is that this is degrees Celsius, mean temperature predicted by the models, if we hadn't added CO2 to the atmosphere or other greenhouse gases. And then if we had, the blue is uncertainty, the red is the uncertainty bounds, and the black is the actual record. So the actual warming temperature record is in fact consistent with the models and not consistent with a model in which you lack greenhouse gases. I should have pointed out, but I think didn't. Oh no, I did point that out, that's good. Okay, so this is a picture of the current model, or system model, from the Geophysical Fluid Dynamics Laboratory located in the Forrestal campus. Over here, it's a NOAA facility, but there's a partnership with Princeton and has been for 50 years now. And what they do is they discretize these things called the Navier-Stokes equations and run them with atmospheres and the oceans and the land. You start with a spinning ball in the dark, turn the lights on, and wait for 1,000 years. And the climate and the ocean currents and the land biosphere, everything just self-assembles due to the internal mathematics of the system. And they currently are able to give you the climate within about 1% everywhere in the world right now. It's actually a stunning achievement, but is a complicated effort. It's like 100 PhDs working full-time for 50 years, right? Okay, a lot of teaching goals here. Take a look at them. As I said, this is the most science-rich of my lectures, but it is, in fact, in 1 hour, the scientific case for dangerous climate change. Thanks a lot. See you on Wednesday. And it's going to be cooler starting tomorrow.